Okay, so now, so obviously, if I look at motion graphics, right, there are lots of different things which are changing here, right? The brightness changes, the composition changes, the point of view changes, and because because some of these techniques would actually be quite complex. Some of these things will be quite complex to measure, but everything is possible. But right now, we're just going to do some very simple things, right? Because the idea is that even with very simple measurements, you can still get something, right? So let's basically do, again, the most simple thing, which is just brightness. Well, you get something, and if you look at this, you can say, well, obviously, this is not measuring all visual changes, right? All visual changes in the image. But it basically tells you, I'm sorry, in the video, but it tells you something about the video. Okay? What does it tell you? Well, we can only know it if we compare this video to something else. Okay? So let's go open, for example, something else, which should be a shot from a feature field. So we're going to go and open something from the field by, this is I happen to have on my hard drive because I've been working this a lot here, is something from a Metamediji camera, multiplied actually to vertical. Okay, so think about some kind of shot. I'm not even sure what this shot would be, but let's try to find out. Very small. Okay, so here it is, right? So typically, you can say, okay, it's typical city field, but it's also a typical cinema, right? It's live action. So let's measure this, see if we can do that. Oh, okay, that's it. Wow. So one thing we can say right away is that there's much more movement, right? Lots more visual change in the motion graphics piece. Okay? So that's something to consider here. In fact, and now let's do more. Okay, so we can say, okay, so we can do brightness, but is there a way to actually get at the amount of visual change more precisely? So let's try something. Let's take this piece and make a copy. Okay, so we can duplicate this. It's the exact copy, okay, same thing. Now what we're going to do is, here's our copy. We're going to take one frame out from beginning and from end. Because what I want to do is I want to make exact copy of my video, but with like one frame displaced, right? So it's like one frame behind. So frame 1 here will be frame 2, frame 2 here will be frame 3. Let's do that. So I'm going to go and delete this particular slice, but we can't even save. I'm going to go here and delete the last slice, the last frame. Okay. And what I'm now going to do, I'm basically now going to measure, I'm basically now going to generate a new video which should only contain the differences. Okay. So let's do that. We're going to say image calculator. So this is our first piece, this is our second piece. And then I'm going to basically subtract frame 1 from frame 2, frame 2 from frame 3, and so on. And you can see this. Okay, so this is basically now we got the third video, which only contains differences. Which actually doesn't contain anything. Okay, that's interesting. It doesn't work at all. Okay, let's see if it does. Let's try again. That's interesting. Okay, let me try to maybe subtract one frame. Maybe. Yes.
On the subtract screen.
Yes.
You,
I didn't choose the
selected both
right.
the same.
Okay, thank you so much.
I would explain it.
Explain it, right? Explain it. Okay, perfect, right? So now we're going to get this. So I'm going to make the video. Now we're going to make the video where pixel black, it means there is no change. And if pixel is white, it means there is a change. Right? So here we go. See?
Wow.
Nice, right? Okay. And now what we're going to do is that, basically all I'm going to do is I'm basically going to measure the average gray tone of every frame, which will tell me how much change it was from frame 1 to frame 2, from frame 2 to frame 3, right? So we can apply the same thing, but we're now going to apply this process to the difference image. Okay. So it goes on like that, right? I mean, basically, I'm showing you like the most simple techniques and the most primitive. And basically, you kind of build up on that. And before I go to manga, let me just kind of show you what happens if you actually try to do something interesting, right, with these techniques. And then we're going to come back to manga. So give me 1 second here. Okay. Perfect. Okay. So for example, okay. So what we did here is we took the data for 1,100 feature films from 1908, from 1900 to 2010. And the measurement on the right side is the average shot length, right? So it's basically what is the average length of a shot. And to do it, you sort of measure the length of every shot, and then you divide it by the number of shots. And of course, what you find if you make this linear trend line, not surprisingly, that over time the films become faster, and and we don't have enough data here, right, to really understand when it happens. So maybe it happens. So the question would be interesting: is does it happen in the 90s because of MTV? Or is it happening all the time? And then what we did is we sort of labeled particular points. So you find that of course Griffith is right here on the trend line. So is John Ford, but so is Jim Jarmusch, for example. And then the Russians really kind of framed this graph. So here's Dieter Werther, manual movie camera, 1989. Here's Tarkovsky with Sacrifice. So then what you can do is you can say, okay, as opposed to looking at all the data, let's only compare films from France, US, and Russia. So the red line is Russia, Soviet Union. I'm sorry somehow, I'm not sure my Chinese team is doing it. France became green, and USA became blue. And I think we find these very interesting patterns which indicate that how culture can sort of follow the social changes, right? So now, again, if we actually have data from more fields, these graphs could possibly change, but I'm not sure it's going to change that much. So what you find out is actually the French films, already after the war, become much slower than American films, right? So by 1990, let's say the average American film in this data set has a shot which is 10 seconds, and the French film has a shot which is 20 seconds, which is probably partly explains why 97% of French films today are made with a government subsidy, and we don't do so well internationally. Now, with Russian films, you get this crazy kind of twist, which you can see reflects, right, the crazy twist of Russian social history in the 20th century. But we also reflect, of course, a particular characteristics of our data set, which came from a website started by film historians, where we actually people can do these measurements and then put it in this website. And so what this really represents is not objective history of, let's say, cinema in these three countries. It represents this history as contained in particular films, which, let's say, film critics and film studies people think are important. So this is why you have this kind of drop with Russia, because of course in reality, if you ask what did Russian audience actually like to see in the 20s, we all went to see American and also Russian kind of comedies and other popular films. But in this data set, you have too many films by Werther and Eisenstein. So that's why you have this drop because of the Russian montage. But I think this part of the curve is more realistic because when Stalin comes to power, right, and he says, okay, now everybody has to make works in a social realism style. Nobody really knows what he means, but what people basically start doing are more kind of Hollywood films, except they're very, very slow. even more slow. And this is the time I was going up. Let's look, I have to get out of this country because things just keep getting slower and slower. Then you can see how after perestroika, things become much, much faster. Let me show you one more thing and then we can go to Manda. So in this case, what you can do, for example, I'm comparing two films by Didier Vertov. So the film, the bottom is a man in a movie camera. So his famous avant-garde film from 1929. And the graph on top is from his film from previous year, which was less experimental, more propagandistic, called The 11th Year. And again, in this case, each bar represents one shot. So the reason that the lower bar chart is longer, not because the film is longer, but because this film has 1,800 shots and 1,850 shots, and this less experimental film it has 650 shots, and then each bar represents the length of a shot. And right away you can see certain patterns, which are really unique characteristic of this film, and of course we can zoom into it, but you can see how certain places, like where shots get shorter, right? Now you can also see that, the cultural critics, right? We tend to see meaning, instruction, everything, but you actually find out that at least in this dimension, and this is actually something you can measure mathematically, there are certain parts of the film where there is no the shot lengths don't follow any pattern at all. So it's pattern in some parts, but not in other parts. Okay, and then what we find here is, of course, overall the shots are longer, and there are some really long shots, but overall, for example, you can say that this film is not so different, right? And you can, as you add more and more films, it becomes more and more meaningful. Let me just kind of finish this look at this film. And then this is, okay, and then we're going to skip this. And then this is basically, so this is using exactly the same technique I just showed you. And I haven't really done this, right? I haven't really done this on a larger data set. So I simply apply this technique to 4 different types of media and culture, and moving image culture, just to see what will happen. And again, what this graph represents are, so I think I took about 5 minutes from every object. And the graph simply represents the frame differences, right? So what's interesting is the progression of, let's say, the progression of how much films change over time, right, in 20th century. So this very kind of quiet graph at the bottom is, of course, the most avant-garde film of the 1920s. This is a manual movie camera. The next graph, which obviously is more dynamic, is Baby Book cartoon from 36. Even here are motion graphics, right? So you can see that the multi-visual changes in motion graphics is much, much more dramatic, and it really goes much above 20th century cinema. Which is, again, not surprising, we know that, but it's actually interesting to be able to look at this quantitatively. So there is much, much more. In fact, I'm going to leave the best stuff for my lecture on Friday, but I think this gives you a little bit of idea what you can do with very simple techniques. And now I'm going to go back to the Manda report.
Couldn't some people say, actually, that the 2 motion graphics are more homogeneous because of their constant oscillation?
Why?
Because contrast is always scale-based, right? And in the narrowly moving camera, there is something that seems to be aligned, there is small modification.
Mm-hmm.
And in the others, it's more...
Well, it's changing all the time.
So it's changing all the time, but there is, because of this, there is no contrast between the changes, maybe. You know what I'm saying? So
Yes, I know exactly what you're saying. Well,
I mean, maybe it's one of
okay,
those...
you're absolutely right. And in fact, you're absolutely right. In fact, let me show you what's going on. Let me show you why this is the case, right? Show you why this is the case. And in fact, we might as well finish this example. So give me a second. Let me show you this example. Because what happens is that if you actually do that, you're going to find out that even though these films, these avant-garde films, supposed to be all about motion, the mostly, significant part of the shots of the films are just still frames.
Yes.
So to that extent, the motion is really in a band, whereas now it becomes the norm, right? Let me show you like this. Let me show you this typical. I had a whole thing on my hard drive, but I just deleted this because it's a 1 gigabyte. But let me kind of show you just one example here. Okay, now we have this basically series of stills. Oh, okay, then this is still, now we have motion. Still, right? Motion, so he actually alternated with still motion, right? But obviously motion becomes like an event, right? A signal. While I was displaying, I actually want to see if I can find something. Because I actually measured motion in this segment, and I got something really, really interesting. Let me see if I can find it. Well, basically what I did is what I found out is that what I was doing earlier turns out to be not very useful because it's useful for motion graphics which have no shots, but if you, in film there's so much change that what I started doing instead is I would actually average the amount of movement per shot. Yeah, let me show you.
Because there's so much cutting.
And well, no, because with motion graphics, because it's done on a computer, you can actually control exactly like the brightness and the colorable elements. Well, in the 1920s, you couldn't really do it. So even though he obviously has lots of structure in his film, he can't completely control everything, and that's why there's just too much variation from frame to frame. But let me just finish this one example, and I was going to kind of preserve it until the future, but I guess I might as well show it to you now, just to finish with this film analysis, just to see okay, so because in the beginning it didn't look very useful, so you can measure the amount of changes from frame to frame, but if you keep working this, here's what you can get, and I'll just show you this in Flickr because this way you know where these things are. So my account, the account on our lab where we put the stuff is called Cultures. Okay, so here's all the visualizations. And let's see if we can find dirt up here somewhere. Okay, so here it is. Okay, now it's going really slow, but if it doesn't load, then I'll show you from the hard drive. But basically, this is really slow. This one's up, that's really slow, so I guess I'll show you from the hard drive. So here's what's going to happen. I see. Right. Yeah, the reason, guys, I don't put it all in PowerPoint because some of the images are 300,000 pixels across. Okay, so what I've done is, I know it doesn't look so sexy yet. What I've done is I basically measured the whole film. I mean, of course not by hand. And then what I did is a program did it. And then I averaged this amount of motion per shot, right? So for example, let's say there's a conversation between us. So sometimes it will go like this, but there's going to be just one big change in the whole 5 minutes, so overall the number will be very small. Whereas, for example, if we go to Times Square, if we came outside, overall the average is going to be quite big, right? So I've done it for the whole film. And so for the first time, you're going to basically see the kind of patterns Vertov, any filmmaker, established in his film, and it will become really hard. It basically will be hard to notice these patterns, without technology, right? So let me show you what's going on. Okay. And so what we have is, okay, so what it is it's a kind of basically I wrote this program and then I just keep modifying it in Metamediji. So each frame represents one shot. Okay, one shot. Okay, and what I've done is I took actually second frame of every shot, And then each bar, the bar underneath the frame, represents the average amount of movement or visual change measured in the way I just showed you by basically doing frame differences and then measuring the brightness and then averaging this over time. So what you're going to find is basically certain patterns which are completely to be expected because, you know, this kind of parallel montage, right? For example, here, and I'm sorry, I should have brought you this film. So what you have is, intertitles, and then intertitles are parallel, right, with the shots of the bank of a river shot from a moving boat. So of course, there's going to be no motion here, some motion here. There's going to be lots of places like that, like this kind of parallel montage, which are, you can say, well, like here, for example, right? If he alternates between two different shots, and some have lots of motion, some have less motion, and it's like normal. But then what you're going to see is some absolutely amazing patterns, which probably what I think is your brain actually registers from, but consciously I don't think you actually notice one. So let me show you some example, right? Okay, so we find it. But again, these patterns are not everywhere, they're in particular parts of the film. Let me show you some examples. Okay, look at this. It's unbelievable. I mean, look how smoothly the motion goes down and the motion starts going up. Okay? Again, I should have brought this film as a QuickTime file and we'd actually be able to look at the actual video, but it's completely amazing, right? And then there are maybe a few other places like this. Okay, not everywhere. Because you would expect this with bars which is go up and down randomly. Okay? So, just to get back to your question, right? So I think that, so this is I think exactly why visualization could be really useful, because it allows us to describe, right, some very important properties of culture. Of course, movement is just one example, which are on the one hand are just very hard to study in language, but also for me that we notice. So this is what you can get, and it's also example, how you can just take one very basic technique and get something interesting out of it. Okay. So I'm going to go back to manga, right? Because the manga work, the manga presentation is basically going to go back and forth with theoretical concepts and visualization techniques. So that was basically just a very long sideway about image processing and how we can use it for cultural research. Okay, so let's go forward. Okay, so what we've done is we basically, in the same ways I showed you, we wrote more sophisticated software, which actually can measure up to about 60 or 70 different features. You can measure colors, etc., etc. And we run the software with this 1 million manga images on supercomputers. And we just measured these 8 parameters, 8 features. So brightness is obvious, standard deviation is obvious. Sobel is a very popular edge detection operator. So it's something you use, for example, in Photoshop. You do command find edges. And in our case, we simply recorded how many edges the program found. Contrast is obvious. And then these other features, which are less obvious, entropy, correlation, energy, it's basically different measurements which are used to calculate the texture. So for example, the entropy in the opposite of information. So entropy simply means that you can say, well, if I have an image which has just few areas of different color, the entropy of this image is going to be, the entropy of the image is going to be very high, information is going to be very low, because I can predict the value of the next pixel, right? Because most pixels don't change. Whereas if you have a kind of photograph or a drawing where each pixel is going to be different, information is going to be very high, entropy is going to be very low, because I basically can't predict the value of the next pixel. So it uses protection. Okay, then we've done some other stuff which is probably not so interesting to you, but this is more for people who actually do this work. We had to kind of clean up. We're still in the process of cleaning up this data because we realized that there are lots of color pages which are kind of going to throw our analysis off. And then eventually, this just talks about different software, which I'm going to slowly show to you. so we use some open source software and we run different programs which we build in Civil. Okay, so how do you read manga? Well, you can go and look at it like this, and maybe if I'm sure that if you look at hundreds and hundreds of books, you'll find some patterns, and of course, you probably may find some interesting things to say even if you look at one book. But what will happen if you actually use software to read manga? So you then need to have a little bit larger displays. So we have this small display in our lab, and we also have access to much larger display, which I'll show you later. This is a small one, so it's 12 screens, and we wrote a special software which runs on this display. So this type of displays are called tile walls, and so we can both look at very high resolution images. We can also do our things, which I'll show you a little bit later. So here we display static visualizations created with my program of 1 million manga pages. Okay, so I'm going to use some metaphors, right? And my metaphors are going to come from astronomy and also from biology. So I wanted to render this 1 million manga pages almost as an astronomical universe. Okay, so this is a typical visualization. So each page is one point, and the pages are organized by visual characteristics. Okay, so in this case, the x is the standard deviation and y is entropy, and in a few minutes you'll see what it is, right? So if you have, what you see here is that there is a particular shape, right, to this manga universe, and obviously you have many more pages in the center with particular values, and then we have fewer pages here. So now I said, okay, let me try to define some concepts which we can use to talk about kind of visual style, which would make sense if we're going to compare like 1 million or 1 billion or 1 trillion artifacts. So I'm going to introduce you guys to some concepts which it's very much work in progress, right? So not new comments. In other words, here's our manga universe, right? So here's, just to show you what it is, let me actually show you a version of the same thing in images, so you understand actually what this is. Sorry. Just give me 1 second. Okay, probably. So here's manga. Here is. Here. Okay, let's see. Right, let's see some manga. Okay, so here's manga. Just a second. Okay, here we go. Okay. Okay. No, this is how big this image? It's big one. It's 1.5 gigabytes. Okay, let me open a smaller version of this. Or we can open this in Photoshop. It's okay. So let's open this image. Now, I don't have the image in my hard drive, but it's on Flickr, where I rendered 1 million pages. So here I just took first 10 titles, it's only 50,000 pages, but it kind of looks the same. Let me open this in Photoshop. Okay. So this took about 4 hours to render. And to render 1 million pages took on it, but we have like a very low very basic iMac, it took 2 days. Yeah, it's 48 hours. So actually, if you go back to our Flickr sites, all these images I'm going to show you are here. So here but it'll probably take forever to. Yeah, so here's the same thing, but here's actually 1 million pages. And of course, in Flickr, like I found the kind of image bigger than 1,000 pixels, so I had to reduce it. Okay, so, but here it is, right? So let me show you actually a smaller version in Photoshop.
So all the pages analyzed are in this TIFF?
Yes, yes. Well, no, the one I'm going to show you is not every single page, but just first 10 titles, so it's about 50,000 pages. And this is the image which has every single page, this one here. So that's every single page, but it's of course a smaller version, right? But of course what you want is you want to be able to do this dynamically, right? but there is no system in the world yet which would allow you to interact with this kind of data yet. So it's actually, they're not quite there yet. But we can do some things. Okay, now let me see if we can get some open. Maybe it's anyway, maybe partly have to close some things, maybe. It sounds like I need to get like some little something computer just for a class, right? Open these things. Okay, let me close this one. So this is so deep here.
I have a question.
Yeah, please go ahead.
Isn't Jonathan Harris's work interactive? Isn't that dynamic? Like
Yeah, it is. Yeah, it's a website which is dynamic website. Yeah.
Okay.
Yeah. But he's not showing images; he's just showing recordings, right? So recordings you can do that.
Oh, okay.
Yeah. So what we have, some the others we have this something like this, which is much bigger, and but even this is not big enough. So we have also big wall. Oh, guys, I'm sorry, it's not everything is. Yeah. So this is so this is not you don't see the whole thing, but this is right now the highest resolution visualization system in the world. It actually theoretically consists of a limited number of monitors. So right now we have 80 30-inch monitors. So the combined resolution of the system is like 8,000 pixels by 40,000 pixels. Behind it is like a dozen PCs with high-end graphic cards. And then we develop a software which allows us to kind of actually, so a few thousand images you can actually interactively make graphs, but you can't do it still with 10 million images. Okay, let's go to Photoshop and actually let's see what this manga images.
Excuse me.
Yeah, please, go ahead.
When did you install that wall of monitors?
Well, it was not, it's not my lab, it's basically been designed by another lab, and we just got a grant 2 years ago which allows us to collaborate. But I think we started to, there's also a different system which was designed much earlier in Chicago. I think we started working with the 90s already.
The 90s?
Yeah, the 90s. Okay, so this is it. So this is now, this is of course a particular view of the manga universe, defined by particular features. So let me show you what happens here. Okay, so in fact, there's something here. This is navigator. So, this is terrible. Okay, let me just do it like this. Okay, so let's start zooming in. Okay, this is nice. One part. Start zooming in. So around 25%. Okay, so here we are. Okay, and you can say, yeah, okay, so basically just just some kind of collage of what's so interesting about it. What's interesting about it is that these features which we measure pick up different characteristics of the image. So if you take all these pages and you project them onto the space with features, and if you've done it, you have to experiment, is that in some cases it organizes all the pages by their visual qualities. So let me show you what's going on here. Let's go back. Okay. Well, promise now we need like neural bar to be able to make sense of it. Okay. So what is this? Okay. So X is standard deviation. Okay. So standard deviation means that the pages which are going to have lots of black, lots of white, lots of different tones, are going to have a big standard deviation. In pages which only have like one tone, are going to have small. Let's check that. That's what you find. Okay. So what you find is that if you go to here you get pages which have lots of black and lots of white. So the spread of the data is quite big. So pages are high contrast. And here, we actually lost everything, but it was zoom out, right? So here, what we have here is we have to go here. What you have is actually pages which are, for example, something like this, right? Where you just have like some black lines and nothing else, right? So mostly just white, right? Or for example, you have a title pages, right? And then here you have something in between, right? So you have lights and a little bit of gray, but not no black. So that's X dimension. You can say, okay, that's kind of useful. But then what's our Y dimension? Well, Y dimension, as I explained, that's entropy. Entropy is the opposite of information. And information, as you know, was mathematically defined by Claude Shannon in the 1940s. It became, this mathematical theory of information became one of the most influential, I think, paradigm of the 20th century. Information is basically defined in a probabilistic term as probability, right, of a value which is going to come next. Like why? Because information theory was developed out of industrial engineering research to figure out how much you can compress television signal or telephone conversation and still communicate it successfully, right? So, as you know, how this compression works, you basically throw away some information, right? So, for example, the way JPEG compression works is you take a pixel, look at the next pixel value, look at the next pixel value. If you notice that all these pixels have a similar color, you just write it down as one color, in this way as opposed to writing values for 1,000 pixels, which is ranked by number, right? So this is how mathematical theory of information developed out of these considerations. So information is basically how unpredictable the next value is. Right? So we go to Photoshop and we make an image which is going to be a random noise. Right? You make an image which is going to be. Okay, why can't we make an image? It's interesting. It's actually interesting. Why? Oh, okay, because I think it thinks I'm good. It thinks I'm writing something here. Right? So if we go and make a new image like this, right? Make a new image. Whoa, I'm so nice. And just go and basically apply noise to it, right? Apply noise to it. Okay. Like, this image actually from a mathematical point of view has lots and lots of information because you really don't know what the next value is going to be, right? Whereas, for example, if you do this, right? If you do this, right? And, sorry, if you do this, right? This image is going to have very little information. Why? Because if you look at this pixel, the next pixel value is the same, so you can basically predict it, right? I just myself only kind of figured it out last week, so it's retrospective. If you don't have it together, it's okay. But just for interest. Okay, so what's going to happen here if we go back to Photoshop, is that the images, the manga pages, which are at the bottom, are going to be pages which have low entropy, which have low entropy. So I think I got it wrong. Sorry. Okay, low entropy, which basically means that what does it mean? Well, let's find out what it means. Okay. All right. Let's go find out. Okay, so let's go find out. Right. Let's go find out. Okay, so let's go find out here. Okay. So basically pages which have very high contrast. And why do we have low entropy? Because this whole area is wide, right? So you can basically predict what's going to be the next pixel, right? Like the only moment your prediction is going to break is here. And then as we start going up, you're going to start seeing more and more detail, more and more gray tones. Okay. See, slowly you start seeing more gray tones and more detail. So this is just, the point is that. The point is, don't worry about entropy in modern mathematics. The point is that you can, when you write, but you can basically use mathematical operations and you can measure some very kind of important properties of images with these techniques, right? So we keep going up, and what we see is we have images which have more and more detail, right, and more grayscale. So you have basically three things which are changing because they're connected. There is more grayscale. This grayscale is basically typically used, right, to create more details because the images are more realistic. They are less cartoony. And of course, to make an image like that takes much more work because you have to fill all these textures to make an image like this, right? So there's also kind of labor which is encoded in these visual properties, right? Okay. So, well, I don't think, we're not used to looking at culture this way. So let's see if we can figure out some kind of language. So here the language comes in as a way to start talking about the space, right? And you can mention doing it, every single film ever created and like all the graphic design created in the world to do, potential, all the architecture, etc. Okay. So I kind of started to come up with some concepts. Oops. So this is exactly the same image, except here it just points, right? So I'm going to define style space as a space of all possible variations, right? So we can say that everything inside this particular shape, right, is a style space. Now, why the style space is inside the shape? Why, for example, why we possibly can't see anything here? I'll tell you why. So what I did is I made this like set of artificial images because I wanted to understand like what is the possible style space in terms of these two particular features. And what happens is that the mean, the brightness, and standard deviations, they're correlated. Right? So after I made this set of artificial images, measured them, projected them into the space, I realized that it's impossible to get anything here because these values, they kind of connected. So that's why we can say possible style space for any image that human can create would lie inside the semicircle. And of course it would change depending on which variables you're going to use, right? So we can say, okay, now if you look at these images which are artificial, you can expect that, for example, if you go and take like every single photograph on Flickr, or if you just take random one-way images created by human beings, you may expect that the space will be kind of filled in an even manner, right? That we may get lots of light images, lots of dark images. Well, what do we get in the case of manga? Okay. Let's go back. Now, we're now going to, this is going to be very scary because it's going to be reductive. And I don't want to say that this line of reasoning which I'm pursuing is going to explain it all. Okay, it's simply a particular, let's say, new method which you can add to other methods to exist. So of course style is much more than that. But from a point of view of visualization and this mathematical representation, we can say that the style would be simply a part of a space defined by particular values. Okay, so for example, we go back to Photoshop, we can say that, again, let's do our favorite operation, favorite intellectual, right? I think I should write some article about zoom criticism, right? Or something like variable criticism. So you can say, well, if you actually zoom into this, okay, and if you look at these pages, you can say, well, this is one style, right? So you have lots and lots of contrast. Okay. And when you go over here, right? When you go over here, you can say, well, that seems to be a kind of different style, right? Because you have much more gray tone, much more gradation, much more detail. Now notice that we're only looking at 2 dimensions, right? So this is not talking about, for example, line character, right? Or 3D versus 2D, right? Because we only have 2 dimensions, because 2-dimensional graph, so we can only talk about some visual properties. No, I can have calculate 3D absolutely, but I haven't done this yet, right? Because it's just 2 ways to do it. But
my curiosity is about the authors. Do the authors they cluster inside?
That's exactly what this is. Well, wait, no, I think.
Okay.
I'm not sure we'll get there today, but definitely tomorrow morning. That's exactly what we're going to ask these questions, right? Okay. All right. So let's go and now ask some questions. Okay. Cool. Okay. So we can say that the style. We can say that the style, again, in a very temporary fashion. And I hope that by the end of the class we can refine it. We can say that simply it's a part of space defined by a range of values, right? So we can say that, well, and again, what is the range of values? You can have to look at these images, right? It depends also on your perception. Except this is why I have this little mark. Because what I will say is that I don't think you can determine it theoretically. because I think that your perception of style really depends on your context. For example, we can say, well, how many objects are in the space, right? Because, for example, if there are lots and lots of objects here, you can say, well, maybe it's all on style, right? Depends what you compare it with. I think it also depends on your style literacy. So we can imagine that today, let's say, you're looking at Mondrian and Kupka, and they look very different, but maybe some bourgeois viewer would go to exhibition at MoMA in 1935, was terrified because it was all abstract art, right? So for this person, the style differences do not exist. So while I think we can define style mathematically, parts of it can be defined because I think it really depends on the content, right? So I would say that a group of artifacts, which by themselves, for example, can be divided into a few styles, it appears having one style if other artifacts added to the space, right? So for example, let's say you only have artifacts here, so then we'll zoom in, and maybe each of those artifacts would be a different style, but once we zoom out, it all begins to look like one style, right? Okay? So now I'm going to, this is like, I'm basically had fun with this. I said, okay, I'm going to talk about mass, which is basically, here's all the actual points which exist. So we can say, here's our universe, and here's all the stars which exist. Or here's a space of possible variation in biology, and here's like all the kind of plants which have been realized by evolution. Okay? So this is all the points. And finally, I'm going to talk about density, which is, well, how many artifacts do we get by a particular region? Okay, I'm not at all sure about these terms, but it will help us to move forward, right? So obviously this area is more dense, this area is less dense. Okay. So now again, so to explain to you, to explain to myself, right, what's going on, I made these artificial images and I project them into this measured one. And in principle, right, you can say, well, if we take enough images created by human beings, right, and we all go take enough photographs, the space is probably going to be filled completely evenly, right? So what happens with manga, right? Well, we can say that, for example, if we have small number of images, created by particular artist, designer, architect, etc. Well, we would expect that they're going to be different from each other, and we're not going to expect that the space is going to fill completely. So what we're doing here is we're projecting Mondrian. So this is some paintings by Mondrian from 1904 to 1917. And this is some paintings by Mark Rofka, about one-third of his career, one-third of his production, from 34 to 1970. We can project them in the same space. Okay?
Using the same parameters?
Yeah, exactly. So parameters, I mean, you can guess what they are, right?
So there's not actually a temporal axis.
No, but not here. There's not a temporal axis here. I'll show you the temporal axis in a second, right? Not here. I mean, so so basically I just put two graphs side by side. So x, right? So x is brightness and y just saturation of color, right? Now it will come back to this graph because there are lots of different things we can find here. But what I want to say is that we can expect that the modernist artist is going to produce artifacts which are all going to be different from each other because that's what he's supposed to do. He's supposed to be original, right? Yes, of course, there's the concept of like series or multiple, but in some ways that comes later, right? That comes later. And we can also say the density is approximately the same, right? Now, there's also maybe certain areas where things are a bit more similar, but in general, for example, it turns out that in these particular dimensions, these later dark paintings of Rovka are not so different from each other. But overall, there are distances between all these images, right? Okay. So we can say, well, what will happen if you actually have 1 million images? Well, you maybe expect that just as everything else in the world, right, lots of other phenomena in the world follow a kind of Gaussian distribution, right, where most of the values are in the middle, and then there are some values which are very low, some values are very high. Maybe you'll find the same thing, right, but we don't really know. So we can say that if a mass of our universe is going to have a kind of center, right, something very dense, we're going to say that this mass has a kind of core. Guys, I just made this up. I can make other terms, but it's kind of fun to be talking about art this way, right? Okay, so this is an example, right? So we can say this is an example. So if you look at this, you can say, well, it's actually, so we can say that obviously both Mondrian and Rovka, right? Okay, they are not just completely randomly distributed in the space of all possibilities, right? In fact, as you pointed out, there's a history. So Mondrian kind of starts here, then goes here, goes here. So Mondrian goes like this, and Rovka actually starts here, and then goes here, goes like this. You know, we can say there is no core. I mean, one thing incidentally which I want to point out, when I did this graph, I had this interesting idea about the history of modern art, which I never realized before. Maybe it's obvious to everybody else. So as I told you, Mondrian, right, he starts here, so with kind of 19th century dark paintings. Then his spirit slowly brightens, and then he slowly moves towards this abstraction, which is in fact typical of geometric abstraction in the 1910s, 1920s, with some exceptions. Like, I think you have, of course, people like Kupka, Delaunay, and Kandinsky, you know, who use lots of color, but actually Malevich, Mondrian, and other people, lots of it is just kind of a bit of color white. Now, Rovka, so this is, let's say, 1917. Now, this is Rovka, 1937, 3 years later. So, of course, Rovka starts in a different place. So, because his images are actually, there's a little figuration here, very more surrealist. But usually, he starts in exactly the same place where modernism kind of ends, right? So, he starts exactly here, and then he goes here and here and here, right? You can also see right away what is Rovka, kind of, you can say, what is partly, again, in terms of this particular parameters, we're not talking about the number of shapes. You can say with one difference, of course, is he has his paintings, which are both very, very saturated and also very, very bright. Okay? Well, so what's interesting when you project this different set of artworks in the same space, it gives you like a way to compare them. And that's interesting, I think, because, you know, I mean, maybe you guys are too young for this, but when I, you know, in my youth, you know, like we go to this art history lectures, and I couldn't stand it because, you know, we pull out this, we always have 2 slide projectors, we always compare 2 images. Well, now you can compare 1 million images. Okay? So it's like art history to point to 0. Okay, so let's see what happens. Now, so then I realized, you know, last week I said, Lev, you know, what you should really do, you should really basically project them. You shouldn't just compare them to each other, you should actually project them in the same space, right? It's almost like imagining photographing the food, and you put in some like, RGB markers, so you get the colors right. So this is the space of all possible images in terms of brightness and deviation. So what will happen if I can put Mondrian in that space? Well, it's interesting, right? I mean, he's actually right in the middle, right? And he doesn't completely cover it, but I would say he's very much owns the whole middle of the space, which is interesting, right? So this will be like an image which is completely dark, this image will be completely light, and this image will be sort of, will have lots of gray, lots of texture, so he's like in the middle. And then, here is Rovka, right? So you can say, okay, so we both own the middle, but then Rovka really owns this part, right? And this, of course, was Rovka's innovation, right, in terms of color. So you see, Mondrian doesn't even exist here. And Rovka is always here. Okay, if you want, I can pull out in Photoshop, we can do that way. Right? And then, this is one particular manga title, and you can see right away that something is very different. So this is, you know, small title, 433 pages. You can say, aha! Is this culture industry now? Because we can see that, okay, there are some outliers. So there are some outliers which actually turns out to be not in original manga pages, they're pages inserted by fans into one manga site, where advertisement follow comics. But the covers, there's a little bit of color pages, because every book starts with a color page. But most of the pages are clustered, right, in this area. So we can say that in contrast to, for example, you know, let's say this set of paintings by Mondrian, there is a core. Well, is it because we're dealing with mass culture, and mass culture kind of follows formulas, and this is not an individual artist who's trying to make every painting different from another painting, but even though manga, of course, you know, it's not Hollywood, we actually have individual artists, right, doing these comic books, but you know, it's more like a narrative art, right? So it's almost like a film, where like usually films don't really change styles dramatically throughout the course of the film. Well, you know, we don't know, but what we have is now a fact which we have to interpret. So let's move forward. Now, before we go, so we can say that and of course, if we go back and project all manga images, we can see the same thing, right? We can see that the space is not filled in an even manner. So there are very few images here, and here's the score, right? So most of manga pages cluster in this area. So this is why I can come up with a ideal core, right? So we can say that manga universe has a core, and I mean, how do you define that it has it? Well, basically, you can just select some kind of threshold. And how do you select a threshold? Well, I think that you have to look at these images. And remember, I talked about just noticeable differences. So maybe you have to use a similar concept. You can say, I'm going to look at two manga pages, and to me, like, they look exactly like having the same style. And here's two pages which maybe have somewhat of a difference, and I may find out this difference means that the average grayscale is 120 by 130, so this is going to be my threshold. So you really have to look at this, right? I haven't done this was just an experiment. So we can say that, what do we learn from this? Well, we can say that even on one hand, there's this kind of maybe certain consistent style, but inside this style, it's actually not, because this is very different from this, but inside this style, every possible image exists. Right? So with the score among the universe, every possible image, right, every single variation is actualized. So we can say that maybe now if we start making analogies between culture and evolution, just analogies, we can say that cultural evolution can explore all possibilities inside the part of a style space. Of course, I think it would be much more meaningful applied to the whole architecture. Okay. So this is actually, again, because I kind of want to compare things in the same parameters. So this is space of all possible images. So it's this kind of semicircle. Okay. Now we're going to project Mondrian in the same space. So he's like kind of in the center. Right? There's no Mondrian here. He's all in the center, right? Here's Rovko, so she's actually has a little different distribution. And this actually uses slightly different even. Yeah, so this is one manga title, this is basically 1 million manga pages. Wow, very interesting, right? So you can see that there is definitely a core, and it's a very particular core, right? It's all here. And then what you can do is you can also represent the same information in one dimension, right? So this is a kind of histogram of basically measurements on the x-axis, right? So this is the histogram of x. So as you can see, there's a kind of center. And this is the histogram of the same values in y. So basically just one-dimensional representations of the same data. Okay. Now, let's take a little break from theory. And actually, let's show you how I actually do it in practice. So, take a break. So now I'm going to open another program, which is also open source, called Mondrian. And this is also quite well known, I think, in data analysis. Let's see if there's any kind of controls. Sorry guys, I'm a bit obsessive, so most programs are not easy. Okay. Metamediji right now. Okay. As you know, when you load 1 million points, you can. Okay, so we're going to start this program called Mondrian. And we're going to load 1 million points into Mondrian. Yes, please.
Were you planning on taking a break?
Yes. Now, right? Yeah, let's take a break. Sure. Sorry.
Okay.
I'm so sorry. You have to remind me. Right?
No, I love that. I just want to see how long this
We
will
were
go.
waiting for us to break here.
Oh,
It's there, the break.
break safe there.
3-4 hours, right? Okay, so I'm going to use another open source software called Mondrian. kind of interesting. Unfortunately, guys, it's open source software. It's actually very powerful, but doesn't. Normally, what I find after working open source software for a while, right, is the commercial software has this very polished GUI, but sometimes not very deep, and sometimes open source software has a very shitty interface, like GIMP, but actually has lots of depth. So I loaded this data. So basically, I want to show you how we make some graphs. So it's one. Okay, so if you see the number here, it says 1 million whatever. This is one. So basically, we have 1 million points there. Okay, and right now let's make exactly the same graph as in the book, right? Let's make exactly the same graph. So I want to make sure that it's very obvious how to do it. So you can try it at home. But you know how we say don't try it at home. In this case, like you can try it at home. Okay, so we're going to select count these features, mean standard deviation, and I mean, I also advise you to kind of, if you're interested, try this out, because it's this program, it's kind of, I would say, state of the art in terms of data exploration. And what's also interesting about this program, like you could basically have 3 types of data, right? I mean, 2 types of data. Maybe you could have categorical data, which is actually not numbers, like words, or you can have numbers. And for example, if I select, let's say I select title names, right? The only thing I can do with title names is bar chart, right? So automatically know what graphs to make. If I select value, which is numbers, right? Now I can make a histogram. If I select 2 numbers, right, which are now I can make other type of plots. So it's also like a good way to kind of learn about contemporary methods of visualization to explore data. So I'm going to take 2 numbers, which is mean and standard deviation, and we're going to select scatter plot, right? So it's simply a technique where you take 2 sets of numbers and interpret them as x and y coordinates, and let's make a graph. So here, let's look at 1 second. It's 1 million points. Okay. Now I know it doesn't look like it, so I can change some parameters here. So, force points. Now I have to wait a little bit. Okay, now let's go and make these points smaller. Okay, now we're going to make it bigger. Let's make the graph bigger. Now, what happens when you load 1 million points, after like about 5-10 minutes, it's going to freeze. Let's see how soon we can go, how much we can go. Okay, so here it is, right? So it's exactly like what we saw in the PowerPoint. Now, okay, so you can see the core very well, right? Here's my core. Here's my black hole, Mongo. Now, you can also change the transparency for some very interesting effect, right? So, for example, if I want to make it denser, because there are actually certain points you just don't see because it's like 1 point, it's just transparent, so we can make it less transparent. Very nice, like this. Or we can make it less transparent, so then we can basically just go to see the core. So, nice, right? Okay, so let's put some in the middle. So now you can say, well, we actually measured 8 different visual features. So let's look, for example, let's see if we can make a graph of our features. So we're going to close this one. So for example, so remember that one of the graphs I was showing you in the PowerPoint was this one, right? Was this one which we discussed, right? And I talked about like entropy, which allows us to measure the kind of presence of texture and grayscale. Right? So in this case, this is standard deviation, that's entropy. So let's make the same graph in Mondial. So I'm going to take mean, I'm going to take entropy. Here it is. I'm going to say mean. Okay. Oh, that actually, no, sorry, it's not mean because it's standard deviation. Sorry. Okay. So here it is, right? It's exactly the same. Okay. So again, let's do it. Stand it out. So, I know, so what I'd like to do is like, I do some theory and then I do some practice, we go back and forth, this way hopefully you won't get completely exhausted, right? Because, that's also how my mind works, right? Okay, so I should now go back to practice. So we started with very simple things, right, like Excel, and then with the imaging, now we go to like more kind of, let's see, some advanced methods of data exploration. So that's good. So now I'm going to jump into the head. You can see what's coming. Because so far I'm just discussing properties of this whole manga universe, but just to show you like where things are going to go. So you were asking, right? You said, well, can we see where individual artists are living in space? Okay, so here we have all the artists. So this bar chart of all artists. Now we can sort it by number of pages. So the artists which have not necessarily more titles, but which have more pages inside all the titles will build up, so you can sort it. Okay. And here are a few title names. Okay. So the same thing. And also, what we have is we have title IDs, which is how these titles are referred on this website in the database. And this is important. I'll tell you why. Okay. So this is because remember I told you. Remember when we were actually looking at this website, we have this list of like top 50. Okay, second row list, right? We have a list of top 50 sites of top 50 in terms of downloads. Comic titles to their site. So this allows us to investigate. We can say, well, what are the properties of most popular titles? What are properties of least popular title, for example, right? So we can think about things like this, right? So I'll just show you. Okay. So if you can people also hungry. Okay. I hope it didn't lose our connection, but to be honest. Oh no. Oh no. Oh no. Oh my god, we lost it, guys. What happened when we just lost it? Oh well. Well, let's keep going. Okay, here it is. There she have. Oh, here. Oh, it's loaded already. Here it is. Here it is. Right? So, it doesn't work. But for example, we can go to top 50. We can find out top 50 titles. This is actually referred by the ID numbers, right? Let's go back to Mondial. So this is like why kind of, for example, if you're really going to do it, you should use things like Mondial as opposed to Excel. So one of the key concepts in contemporary data analysis using visualization is the concept of, it has different names, coordinate views or multiple coordinate views. So the idea is that we have a spreadsheet, right, which has 1 million pages. In every page we have this information about author, title, genre, etc., and measurements. Right? So in Excel, you can also make different graphs with data, but the graphs, we don't talk to each other, right? So here what's going to happen, for example, if I select part of the data in one graph, the same data will be automatically selected in other graphs. So let me show you how it works. Very powerful. Okay. So now we know that our titles 2, 3, 4 happen to be, in fact, most popular titles with English readers, as documented by this website. So let's select title number 2. Okay. So first of all, its pages automatically highlighted. Okay, so let's make it a little bit. Okay. And we can also find out that we can find out the name of titles. The name of titles is One Piece. And we can also find out the author of this title. And we can also now see visual properties. So what would you say about? Well, what I would say is that, the distribution, right, formed by all the pages in this title, seem to be quite typical of manga universe, so to speak, as I call this, right, as a whole. Okay, well, this kind of maybe confirms something about the culture industry, right, maybe. Okay, so that's title. Let's say that's the most popular title, or one of, right? That's one of them. So let's go look at others. Bar chart title ID. Okay, so This is one, right? This is one. Now, but again, remember, you're not looking at every single dimension of this title. You're just looking at, for example, the kind of brightness values, right? So that's one title, which happened to be, sorry guys, that's one piece. Okay, this is now one. Now this is bleach. Well, this is already this is different, right? You see how it all goes here. Now, if you remember, what we have, what we have at the bottom of pages, which are more high contrast. So this title obviously has a style which is much higher contrast. It hardly has any pages which have lots of detail, right? So it doesn't use that many textures. And so on and so forth, right? So you can do it in different ways. We can, with standard title ID, you can also, of course, select a particular title here. Right? You can also, of course, select two titles, like this, right? So for example, we can say, what is the space occupied by the top three titles? Well, we can say 1, 2, 3. So overall, right, it's very, very similar. Now, again, I'm going to go into this much more tomorrow, but let me show you what's coming. So now let's look at individual artists, right? Let's look at individual artists. Okay, so this is the titles. These are individual artists. Here's artist. So let's say you're interested in a particular artist, I don't know. You're interested or in a particular title, because some artists actually have multiple titles. So let's say we could take somebody who only has one title. Okay, I don't know. Okay, guys, I don't know that much about manga. I'm learning. Okay, Nikoi Tsubaki. Well, here are his pages. So you can see that again. He has a. We can say that his style is. It's maybe not. I mean, it's not necessarily an outlier, but it's not necessarily the most typical, right? Because you can say that he has lots of pages. Right? If you remember the shape, the images. You can say that he has lots of pages which are mostly high contrast, and there are just some pages which have gray tones, right? So now, notice from this point of view, every artist has his unique signature, right? So now we start seeing how we can actually potentially visualize kind of cultural variability, right? Also like this. And the same thing we can do. The same thing we can do with titles, right? So here's our titles. Choose title 1, title 2. Okay. Now you also start seeing some patterns, right? Okay, you can say why is this title has all these pages here, right? Let's call it color pages. But you can say that it definitely has a core, right? So you can say that most of these pages, are kind of here. And this title seems to have kind of two cores, right? There are these pages here, these pages here. Now unfortunately we're not able to do this with actual images yet. So what I do now is I have to do this. Then I have to go make the actual image with pages. Let me show you how I can do it. Okay, but you see how it's coming. Finally, just before we leave Mondrian, we'll come back to Mondrian. We just sketch the surface. Now, let's say I'm interested to compare the style of titles which are marketed to different audiences. Okay, and remember I told you how there are these 4 audiences in manga. In Japanese manga, it's basically teenage boys, teenage girls, young women, young men. Well, let's find out. Okay, so here is our largest category, which is okay. So we have to make a bar chart. So basically, ones will be all the titles which belong to this category, 0 or not. Okay. And at some point, okay, wow. We can say, well, it's kind of hard to say, but it looks like we're all over the place, so we actually don't see anything special here. Okay, what about teenage girls? It looks kind of the same, although it's interesting that this bound doesn't exist. Well, now, what if we actually look at this, in a different space, right? So what if instead of looking at this dimension, basically we're going to look at this dimension, right? The dimension would be this one. The dimension. So basically, what we're doing now, we can look at this particular features, but what if we look at this one, right? So what happens? Let's go take a look. Okay. So what I'm going to do is I'm going to select these dimensions, mean standard deviation. So basically what you're seeing is also, this is basically how people explore data today, right? The process which I'm involved in, it's called kind of exploratory data analysis. So idea was developed very recently, like in the 70s. And of course it also has to do with development of computer graphics and computer-based visualization. But you can also do it in paper. So the idea is that when people get a very big data set, in some cases you have no idea what's in it, so what you want to do, you want to explore it, form some hypothesis, and then later you can actually do statistically test this hypothesis. And that's what we're doing, which is playing around. So let's make this graph. Let's here it is. Okay, it's symmetrical. So basically what we're doing right now is it turns out we don't really understand what some of the measurements we've done actually represent. So we're now trying to figure it out, which is taking us months, right? So it's not, I mean, it took a while, it took a year to get to this point, and it's very easy. It took some time. Okay, so let's look now at our 4 categories. Okay, so this is teenage boys. Okay, well again, I mean, you don't see anything special. Okay. And these are the teenage girls. The girls you don't see anything special. I mean, so okay, so actually it turns out that if we're going to look at like, all the pages, right, which belong to these categories, I mean, I actually don't see overall much difference, right?
Mm-hmm.
But of course, if you start combining, for example, gender and genre, if you start looking at titles which are particular genre, you're going to see some difference, right? So, for example, you can say, okay, here's, we can go and say, and we'll do it later, right? We'll do it later. Because I also need to look more closely with genre categories. So we're going to also tomorrow also look at some text visualizations, also some deep network visualizations. So we'll come back to this. Okay. So let's finish discussion of this kind of just the properties of this overall monkey universe, right? So finish this topic. Okay. So what I basically get out from these graphs is this proposal, right? And remember we said, well, just to kind of repeat a little bit, right, review, we can say that, so here's the space of all possible images defined by the semicircle, and we can say that, so this is style space, and we can say that a particular style will be pages, will be images which occupy a particular part of the space, and then we talk about the mass, and then we talk about density, right? Okay. So what's interesting is that like in this area, right, it's very, very dense. So almost every possible variation is realized, right? Okay. And it's something which is discussed, right? So if you remember that the pages here have very high contrast, and the pages here, right, have lots of texture, lots of detail. So if you look at any particular title of an artist, you may find, but I don't know for sure because I'm also in the process of exploring this. This is what I do every night before I go to sleep because it's so much fun. Right? So we can say that particular titles or particular artists or particular genre are likely to occupy particular parts of the space. So they probably have particular styles. Although I'm also finding there are some titles where the style varies dramatically. But if you think about the style overall in manga, you can say, well, actually, it's a completely continuously varied quantity, right? Why? Because there are not really any natural breaks here, right? You basically go from no texture and no detail to lots of texture, lots of detail in a completely continuous way. Right? We kind of go back, right? So you remind you how, okay, I'm not going to do all this big English, don't worry. So all this small version. Which means that maybe our concept of style is problematic. Okay? Okay? That if you're talking about a particular let's say, cultural phenomena, cultural artifact, you know, a particular painting school, maybe, I don't know, deconstructive architecture, etc., you can say, well, there's a particular style, there's a particular commonality, but let's say if you maybe start enlarging your field of view, it turns out that it's something which is actually continuously varying, and if you make breaks anywhere, these breaks will be arbitrary. Let me load a small version of this image, right? Remind me. But you know, this is the point I'm struggling with because partly it's also it's a little bit like a physics, right? Where you know, what you can see depends on the measurement instruments, and I kind of wonder that to some extent it's also a function of my measurement instruments. But let me just show you this one image, just to bring it back. A small image, just a second. Oh, sorry. Okay, going to make like I'm just going to take a small one, so it's less fast. So it's the same thing. So, okay, so remember, right? So basically start zooming in. Let's start zooming in. You can say, well, you know, like, oh, sorry, this is too much. Right. So what you can see is that, you know, as you kind of project all pages into the space, okay, you can say, well, here's the pages which are very extreme, right? So it's only black and white, right? And then here are the pages which are mostly gray tone. We have like lots and lots of fine texture. But in between, it's just a continuous function, right? Like there are no particular clusters. So that's why we can say that in the case of, let's say, manga culture, in fact, maybe we can't really use language to talk about style. Because when we talk about language, we'll have to make cuts. We'll have to say this is style A, this is style B, this is style C. And at least if you look at it this way, it's going to be completely arbitrary. Now, it's probably possible that if we start looking at actually particular titles and particular genres, we can find that, okay, let's say we can find that all titles which belong to a particular genre are here, and all titles which belong to a particular genre are here, but it actually doesn't look like it. So it turns out that we kind of have to rethink some very fundamental concepts which we take for granted, I think, when we discuss culture, such as style, right? And just to finish this point, okay, so this is right what I just kind of showed you. Right? So this is, let's say, the lower part, and that's the upper part, and in between it just continues. Now, at the same time, again, if we look at the same graph, we can say that this universe has voids with some statistic possibilities and then observed in practice. Okay? So again, if you go to this graph, okay, and in the hyperloop, we have these graphs next to us, right? You can say, well, you know, so if you remember, most manga is like somewhere here, right? Why? Because most manga is very light, it's lots of white space. Now you have like stuff here, right? You remember have stuff here because you have lots of gray texture. So most it's like here because it's lots of white space with little lines. So you actually don't have this. Right? You know, where this is what we get, you know, this is what gets filled in if you look at 19th century painting because it's going to be all the dark stuff. So we actually don't have manga, even the titles, right, which are very horror, you don't really have any titles, for example, where most of the pages will be very dark. But okay, so there is void for this universe. Okay. And finally, basically I said, how many things I can say about this one image? I can say that this universe, again, this is also kind of displaying, making some reference to Panofsky, who actually talk about homogeneity of a space is defined in the Renaissance, and how perspective reflects it. You can say manga universe is, this is just like to show off, right? Inhomogeneous and anisotropic, but you can say some directions, some more important than others, right? Some directions, some more important than others. It's basically simply a way to say that This is not symmetrical, right? This is not symmetrical. Okay, so now, yeah, so let me maybe start with the second part. Okay, so now let's talk about this tags. So first of all, what's interesting about this data set in manga in general is that it's a kind of taxonomy which became taxonomy. So what I was told is that these tags, right, horror, comedy, action, etc., originally were defined by fans, and then we have adapted by the industry. So now the industry can use these categories as well. Okay? Now, as I told you, if you go to one manga, there are 35 genre tags, genre categories, and there's only 4 gender categories. And when people assign tags to a particular title, you can assign only one, but in this particular website, there's only one gender tag you can assign. So here's some tags, right? And there's also country of production. Unfortunately, most is Japan, with a bit of Korea. So this is the tag frequency, right? So for example, we have 100 titles which are comedy, 386 titles which are shonen, which is boys, etc., etc. But as I said, what's really important is that the categories overlap. So there are basically just a few titles which only get one category. Right? So mostly titles are like this, right? So for example, One Piece, which is again the most popular title in the kind of manga's history, well, it's tagged as adventure, anime, comedy, drama, and fantasy, and so on and so forth. And this is a graph, right, of tag frequency. So you can see that there is only 57 titles out of 900, which have one tag, and most titles have between 2 and 4 tags. Well, this is very, very interesting because this also complicates the idea of a genre. Turns out that the way this is defined, there are no genres in manga. It's all hybrids. Well, that's very interesting. Okay, so you basically type Brun Latour, and you get his website. And Brun Latour is very interesting to us because she's actually been writing a lot about, been writing a little bit about visualization. And he's also, as I mentioned, running this visualization project called Making Controversies. The students in his classes, which is kind of history and sociology of science and technology, using visualizations to represent controversies around various scientific and public policy issues.